طلاب الجزائر نحن للمجد هنا، نحن آمال الجزائر في الليالي الحالكة، نحن طلاب الجزائر نحن للمجد هنا.
Good morning everyone and welcome to this course. My name is Farid Boutout and I will be your instructor throughout this semester. My academic background is in electronics telecommunications and my main research and teaching interests include antenna theory, computational electromagnetics, and microwave circuits. Welcome to this course, Passive and Active RF Microwave Devices. In this session, we will review the course syllabus, including the learning objectives, course content, assessment methods, and recommended references. This overview will help clarify the organization and expectations of the course. I encourage you to participate actively, ask questions, and engage in discussions to make the learning experience more effective and interactive. The teaching plan and course material adopted in this course are based on the latest updated version of the Master Telecommunication syllabus of the year 2025. The Master Systems of Telecommunications program covers 4 semesters. Here is the distribution of teaching units across semesters. Semester 1. Semester 2. Semester 3. The shortlisted course is taught in the 3rd semester of the Master Systems of Telecommunication program. Course information is highlighted in green color. In the 4th semester, students prepare a master's thesis and defend it before a committee composed mainly of faculty-ranked teachers and invited members from industrial and socio-economic sector. This introductory session provides an overview of the course, including its description, outline, and recommended references. We present a structured overview of the course content by chapter and by week throughout the semester. For further details, please refer to the Master's Program Information Sheet. All bachelor's and master's programs are designed on a 15-week semester structure. The course title is Active and Passive RF and Microwave Devices. Number of credits 4 with coefficient 2. The course video is available on the Moodle e-learning platform of our university. The main objectives of the course are provide the concepts and presents the tools for the design of various RF and microwave devices. For passive devices such as transmission lines, meter wave guides, couplers, power dividers. And for active devices such as FET transistor, Schottky diode, mixers and oscillators. Course program can be divided into 2 parts, passive components and devices and active components and devices. The first part consists of 2 chapters, passive circuits and devices for microwaves and microwave filters. Chapter 1, passive circuits and devices for microwaves. 4 weeks from week 1 to 4. Introduces the fundamental concepts and essential components used in microwave engineering. The chapter begins with the fundamentals of S parameters, which are crucial for characterizing high-frequency networks. It then covers the theory and applications of coupling transmission lines and directional couplers. The chapter further explores key microwave components such as circulators, magic teas, hybrid couplers, power dividers, directional couplers, attenuators, and circulators, emphasizing their operating principles and practical applications in RF and microwave systems. Finally, it presents analysis techniques including S-parameter-based methods and signal flow graph analysis to model and evaluate microwave circuits efficiently. Chapter 2. Microwave filters, 2 weeks from the 5th week to the 6th, focuses on the fundamental principles and design techniques of frequency-selective microwave networks. The chapter begins with the study of periodic structures and their role in filtering, highlighting how our propagation characteristics can be engineered to achieve desired passband and stopband behaviors. It then introduces classical and modern filter design methodologies, with particular emphasis on the image parameter method and the insertion loss method, which are widely used for the synthesis and optimization of microwave filters. These approaches allow the systematic design of filters with specified frequency responses and performance criteria. Chapter 3. Active circuits and devices for microwaves. weeks 7 to 8. This chapter introduces the fundamental active components and circuits used in microwave and RF engineering, focusing on their physical principles, operating characteristics, and key applications in high-frequency systems. It begins with an overview of RF diode technologies, including the Schottky diode, PIN diode, varactor diode, and impasse diode. Each device is studied in terms of its structure and high-frequency behavior. Schottky diodes for fast switching and detection, PIN diodes for RF switching and attenuation, varactor diodes for voltage control tuning, and impasse diodes for microwave signal generation. The chapter then explores microwave transistors, particularly RF implementation of the MOSFET and MESFET. Emphasis is placed on their small signal models, frequency limitations, and roles in amplification at microwave frequencies. Finally, the chapter covers key nonlinear microwave circuits such as oscillators and mixers. Oscillators are presented as fundamental signal sources for generating stable RF and microwave frequencies, while mixers are introduced as essential components for frequency conversion in communication systems. Chapter 4. Gain of quadruple, weeks 9 to 11. This chapter focuses on the fundamental concepts used to characterize and analyze the performance of microwave two-port networks, with particular emphasis on gain definitions and stability criteria. It begins by introducing the different types of gain used in RF and microwave engineering, including power gains, transducer gain, and available gain. These definitions provide the basis for evaluating how effectively a network transfers power from the source to the load under various impedance conditions. The chapter then discusses the concept of unilaterality, which refers to the assumption that reverse transmission in a two-port network is negligible. The simplification is often used to facilitate circuit analysis and gain calculations, although its validity must be carefully assessed in practical microwave devices. A major part of the chapter is dedicated to stability analysis of microwave amplifiers. It distinguishes between unconditional stability, where the circuit remains stable for all passive source and load impedances, and conditional stability, where stability depends on specific impedance terminations. Tools such as stability circles are introduced to visualize regions of potential instability in the source and load impedance planes. To rigorously assess stability, several mathematical tests are presented. These include the rolled stability factor, K factor, condition, and also known as the K-delta test, which provides a quick criterion for unconditional stability based on the S parameters of the network. Additionally, the mu test is introduced as another robust stability measure that evaluates the proximity of a device to instability. Chapter 5. Amplifier Design, from week 12 to 14. This chapter presents the fundamental principles and methodologies used in the design of microwave amplifiers, with emphasis on achieving specified gain, impedance matching, and low noise performance in RF systems. The chapter begins with the design of linear amplifiers for maximum gain using the principle of conjugate matching. By properly selecting the source and load impedances, maximum power transfer between the amplifier and the surrounding network can be achieved. The analysis is based on the scattering parameters and matching network design technique. The chapter then addresses amplifier design for a specified gain. The objective is often to obtain a desired gain while maintaining acceptable stability and impedance matching conditions. Design procedures involving gain circles and impedance transformation techniques are introduced to satisfy these performance requirements. Finally, the chapter focuses on the design of a low noise amplifier, LNA, a critical component in microwave receiver front ends. Emphasis is placed on minimizing the noise figure while preserving adequate gain and stable operation. The trade-off between gain optimization and noise performance is examined through appropriate matching strategies and device selection criteria. The 15th week of the semester will be dedicated to Chapter 6, Microwave Integrated Circuits. In this chapter, we will introduce the principles and technologies associated with the microwave integrated circuits, MICs, which enable the realization of compact and high-performance microwave systems through the integration of active and passive components on a common substrate. The preparation of this course was based on the 2025 published version of the Harmonized Curriculum Framework, Canva de Programme Harmonisé, Specialization in Systems of Telecommunication. Presented herein is a list of 16 textbooks recommended for further reading on the subjects covered in this course. Some of most challenging examples and problems presented in this course are implemented using two softwares, MATLAB and Advanced Design System. Presented herein are the front covers of the cited textbooks and software packages.